So maybe let me present Aditya. Aditya is a postdoc at UIC, University of Illinois at Chicago, and he will talk about enumerating independent sets in Abelian Cayley graphs. Yeah, go ahead.
Yeah, so hi everyone. Yes, thanks for putting up with this. Thanks a lot for inviting. So this is joint work with Liana, who's currently at LSE. Am I audible? Okay, so let me just quickly get into the definitions first, so we can state the result. G is always a graph which is d-regular on n vertices. Okay, and script ig is the set of all independent sets in G. And little I of G is the number of independent sets in G. So the main kind of questions that we will be focused on is, So we'll be kind of focused on this kind of questions. How big can the set of independent sets, the number of independent sets be in a graph? And we'll be focused on Cayley graphs. So a bit of notation regarding that. F is an abelian group, and F has order 2n, like it's an even order, but it is not important for this result. Right, so just without, it's kind of we'll see that it's kind of without loss of generality, assume that F has even order. And for a subset D, these are called generators. The Cayley graph is defined as, so it's written as F comma D. The vertex set of the Cayley graph are just all the group elements, and the edge set is given in this way. Every element U has neighbors U plus I, where I belongs to D. Right? So this kind of, this is what a Cayley graph is. And because we'll be talking about independent sets, let's assume that G is undirected. That means, yeah, D is negative D. So D is minus D. So if U plus I is the neighbor, then U minus I also is a neighbor. So this is just to kind of maintain the undirectedness of the graph. Okay. So yeah, so if it's a D-regular graph, then the size of this set of generators is D, and the neighbors of the set of neighbors of a vertex is just the set of neighbors of a vertex U is just U plus D. This is again, so this is just U plus X, such that X is in D. Okay, so this is just the set of neighbors of a vertex. Okay, so yeah, so let's recall the notation again. IG is the number of independent sets in G. So the motivating question is, what can you say about the size of IG? Or rather, like, I'm specifically interested in upper bounds. Okay, so pretend that we did not know this was abelian. Let's just say like it was general graph. So these type of problems are very important. Like, so a lot of enumeration problem in combinatorics kind of reduce to either independent sets in graph, or they heavily make use of the upper bounds on the number of independent sets in graphs. So this is what, and a bit of background. Let's pretend that we'll be focused on abelian graphs, but like just assume that G is a general d-regular graph on n vertices, 2n vertices. So there's a theorem of Alone that proves that the size of IG is at most 2 to the n times 1 plus some little o of 1. Okay, so this is little o of 1 goes to infinity, as goes to 0 as D goes to infinity. And the motivating question, this is actually a question of Granville. This result implies that the number of sum free sets among elements 1 to 2n is at most 2 to the n times 1 plus little o of 1. Okay, so, and the point is that, like, you think for a while and you see that 2 to the n is also a lower bound, because like all subsets of the second half of elements are sum free. By the way, sum free means there do not exist A, B, C such that A plus B equals C. Okay. So you don't want, so you want the number of subsets of 2n such that they do not contain any 3 elements, so that 2 of them add up to the third one. Right? So you want to upper bound the number of them. So if you pick subset of the second half of the elements, obviously you will know 2 of them add up to the third one. Right? So also, if you pick the subset of all odd numbers, then also no 2 numbers add up to the third one. So lower bounds of this kind of nature are not very hard to show. The main point here is that it's an upper bound too, like up to the log factor. Okay, so later on, so this is work by Green and Saposhenko. Independently, it's actually ordered 2 to the n. So it's not only the correct answer up to the log scale, it's also the correct answer up to a constant factor. But the point here is that this is a general theme that's going to carry on. All of these objects that we would like to enumerate, they tend to cluster. For example, most of the sum-free subsets kind of tend to cluster among all the subsets of odd numbers, or all the subsets of the large elements, or things like that. So I guess this is a general theme to keep in the back of our mind, like that the independent sets tend to cluster in large groups. And yeah, so this is the result again by Alone, who shows that Ig is at most 2 to the n times 1 plus the little o of 1. And even here, this kind of a lower bound is not very difficult. Just pick up a bipartite graph. So G is allowed to be bipartite too. And so if it has 2n vertices, then each of the sizes of the parts has n vertices. And in particular, every subset of X and every subset of Y are independent. So the number of independent sets is at least 2 to the n minus 1. So again, what's interesting here is that this is tied up to the log scale as D grows. Okay, so but yeah, and this is not this has been improved like around 10 years later by Khan, who showed that for a bipartite graph, the number of independent sets is at most this quantity, 2 to the d plus 1 minus 1 raised to n over d. Again, so this is d regular, 2n vertices. Okay, so where does such a number come from? It comes from the tight example, where you take a bunch of disjoint copies of KDD. This is the complete D regular graph, the complete bipartite graph with D vertices on each side, and you take n over D disjoint copies of them. So the number of independent sets of this is either all subsets of the left or all subsets of the right, but you have to account for double counting the empty set. So this is 2 to the D plus 1 minus 1. And there are n over d copies, so that's where this comes from. So for bipartite graphs, we know the tight example, and Khan actually conjectured that this should hold for every graph. For every graph, the number of independent sets is also this quantity. Okay, and this was proved around 10 years later by Zhao, who proved in this very general form, which says that for every d regular G, the number of independent sets in G squared is at most the number of independent sets in G cross K2. Okay, so what does this mean? What is G cross K2? So here is G and here is K2, which is just a complete graph on 2 vertices. So what you do is, to construct G cross K2, you make 2 copies of the vertices of G. So let's call them G1 and G2. And if you have an edge UV, what you do is you put an edge from U1 to V2 and V1 to U2. So I guess this symbol shows how you put edges between them. So Zhao shows that for every graph, D regular, like for every graph, the number of independent sets squared is at most the squared is at most the number of independent sets of G cross K2. So by the way, like, yeah, so I guess this is a note that will be relevant later, is that if G is a Cayley graph, then even this G cross K2 is a Cayley graph. Right? So G is a Cayley graph on a group F with generator set D, then G cross K2 is a Cayley graph on group F, direct sum Z mod 2, and and the generator set is the D, direct sum just 1. Okay, so if G is a Cayley graph, then even like this doing this operation preserves the Cayleyness of the graph. But anyway, so back to this discussion, what Zhao ends up showing is that you can basically reduce your case, the independence of any graph to that of a bipartite graph, like if you want an upper bound. And so the results of Khan and Zhao imply that for every d-regular graph on 2n vertices, the number of independent sets is this. So in other words, the graph that has the most number of independent sets among all d-regular graphs and 2n vertices is this particular graph. Okay, so this is all you can say if G is a general d-regular graph. So what we want to say is that, like, is this better for Cayley graph? You want to know what more can you say for Cayley graphs? Like that's a pretty like strong structural condition. And eventually we'll see that the point is that the number of independent sets is much smaller in Cayley graphs. Okay, so I'll just state the main theorem. So again, so G is a Cayley graph on 2n vertices and degree d. The main theorem is that if the degree is large enough, which is at least some log n up to some polylog factors, and G is connected, then the number of independent sets is at most 2 to the n plus 1 times 1 plus z law of 1. And this is tight up to this constant whenever G is bipartite, as bipartition x and y, the number of independent sets at least 2 to the n plus 1, right? Because like you can either pick all subsets of x or all subsets of y, leaving the empty set twice. So this theorem says that if G is a Cayley graph, this trivial lower bound is kind of tight up to is asymptotically tight. So this is the main theorem. Are there any questions so far?
I think the G connectedness.
Huh?
G connected means something else here, right? It's not.
No. G connected means just the graph is connected. You can go from any vertex to any other vertex. Right. I mean, and I need G connected because if G is disconnected, like, and it has two parts, you know, I can either pick all subsets of here or all subsets of here. And for the second part, I have a same choice. So I have to multiply with 2 raised to the number of components. So just to avoid all that, I'm saying G is connected. Then the number of independent sets at most 2 to the n plus 1 times 1 plus z law of 1. And yeah, and this, so a question is whether kind of this dependence can be improved to make sure like you fall into these two main categories. And the conjecture is that if D is at least slightly bigger than 2 log n, D is bigger than 2 plus like z law of 1 times log n, and it's connected, then the number of independent sets is at most this number, like 2 to the n plus 1 times 1 plus z law of 1. So these are all again Cayley graphs. Okay. And I'll kind of describe the example that again we think is tight a bit later on. But so far, are there any questions regarding this? Okay, good. So here's like a bit more motivation / like approaching the proof. So the tight example for general deconnected cases, general deregular graphs is kind of highly disconnected. Recall that it's a bunch of disjoint KDDs. So what about like kind of highly connected graphs? So think of like expanders, etc. So these are like very highly connected graphs. So what's happening is, again, for now, assume it's bipartite. Consider bipartite graph with bipartition x and y. And yeah, so the number of independent sets is exactly the sum over all a of x 2 to the n minus the size of neighborhood of a. Right? So to choose an independent set, what do? You pick a subset a of x, look at its neighborhood, all that is blob, pick a subset b from whatever's remaining. So it's exactly this. And you know, just for as an upper bound, I'm just, because the independence number is n,
Aditya? Aditya's internet is bad. He just texted me.
Is this working? So I tried to hotspot from my phone. Am I audible? Is it?
We can see you.
Yeah. So can you hear me?
Yes.
Okay. Yeah. So let's hope that this stays for a while. Yeah. I'm sorry about that. Okay. So where were we? Yeah. So we were counting the number of independent sets in bipartite graphs. So yeah. This is where we stop. You have a bipartite graph with partition X and Y, each of size n, and you want to count the number of independent sets of this. So this is an identity because how do you choose an independent set? Just choose a subset of X and then choose a subset from the other side that's not part of the neighborhood of the subset you chose of X. Okay? And like I said, if you just want an upper bound, you can assume that both of these A and B are at most n over 2. Okay, and with a, just pick whatever side is the largest, and just it's 2 times the larger of these two quantities without loss of generality. That's the A part. Right? So the idea is that if the size of the neighborhood is much larger than the size of A, then this summation, when you're summing over 2 to the minus neighborhood of A, that's small. Right? And that's kind of, so this is something that you expect to hold in graphs like expanders, etc. Okay? So and this is kind of what, this is really the rough idea of what we'll be looking at. So to state what we'll actually do a bit more formally, let's just set up some basic notation. Yeah, for a subset A, we look at the closure of A to mean all the elements of X whose neighborhoods are contained in the neighborhood of A. So it's closed if A is equal to its closure. So this is, so again, like for picture, here is A. Here is the neighborhood of A. So if a vertex has all of its neighbors inside the neighborhood of A, so that's part of A closure. Right? So for some reason, while counting independent sets, these things are better to keep track of than the sets A themselves. Okay, and we say A is 2 linked if A is connected in G square. That means, yeah, so this is just the square of the graph. If whether U is connected to V in G square, if distance of U and V is at most 2. Like, so you connect all the vertices of distance at most 2. And we care about this definition because whenever the subset of X, it's a, like the analysis we'll do really makes use of splitting up the subset into its 2 connected components. So if you have 2 different 2 linked components, then kind of the neighborhoods don't intersect. So So this is why we split them according to two linked components. And finally, we say that a subset is small if not A, but the closure of A is at most n over 2. Okay. So these are the three definitions that we'll use. Are there any questions regarding the definitions or their motivations? Okay, so to continue, let's just assume that from now on, G is just bipartite with partition with parts X and Y. So that's just how G looks like. And if the point is that the independence number of G is n, right? So in a bipartite graph, where each side is has size n and it's d-regular, so the independence number is n. So for any independent set, either its intersection with X or Y is small. So this takes maybe a couple of seconds to think about why this is true, but this is not. Yeah, so the point is that on at least one side, less than half of them should be blocked. So let's just rewrite this part again. The number of independent sets of G is at most, now instead of summing over the smalls, like the sets of size n over 2, I'm just summing over small sets. Right? So there's just a more refined summation. So if we want to show that the number of independent sets of G is at most 2 to the n plus 1 times 1 plus titlo of 1, then we need to show that in this summation, only all of the non-empty sets A, their contribution is tiny. Okay. Are there any questions so far? So this implies that is at most 2 to the n plus 1 times 1 plus the titlo of 1. Right? So this kind of reiterates the fact that most independent sets are just subsets of X or subsets of Y. Right, and to do this, we'll kind of, so the last bit of notation, let's call script G of A and G is the number of A. It's the number of A that are small and two linked, whose size of the closure is A and size of the neighborhood is G. Okay, and let's call T like G minus A, which is, so this is, and this is like the neighborhood of A. The size and the differences of these is, let's call that T, and this is kind of the expansion of the graph or the expansion of the set A. So basically the point is that what can you say about T? So like just using the fact that this is a Cayley graph, can you say anything non-trivial about T right off the bat? And the answer is that you can. So there's a theorem of Olson in 84, which says that if A is small, which basically implies that if A is small, then T is at least D over 2. D is the degree. So every set which is small has a neighborhood size at least D over 2 more than itself. Okay. So, if you're curious, this is what Olson's theorem actually says. So recall, this is some set notation. I'll go over this again. So A plus D, where again A and B are subsets of the abelian group, is just you take every element of A and every element of D and just add them. So this is just a subset of A and D. And the neighborhood of A in the graph is exactly equal to the set A plus D. Okay. And Olson's theorem basically says that either A plus 2D equals A plus D, or the size of A plus D is at least this size of D, at least D over 2 more than A. So this kind of implies that the graph is disconnected. So since we don't want this, we are left with this possibility. So in any case, every set has every small set has a neighborhood size at least D more than itself. So that much. So that's just so this is something we can just say about abelian Cayley graphs without anything. Like every set at least has this much expansion. Further questions? And our main lemma is that the size of GAG, like again, so script G of AG is the number of small sets A, which are two linked, whose size of the closure is A and size of the neighborhood is G. So the main lemma, which is something close to saying that the size of this set script GAG is at most 2 to the G minus some omega T. So this is, at the moment, it's not at all supposed to be clear why this would help. This is just a quantifying, this is a quantifying, this is just something you're bounding the size of sets that have a certain neighborhood size. But the point is that this lemma implies what we want is that the sum from the non-empty small sets of 2 to the minus NA is actually tiny. So I'll just quickly go over the proof of this to kind of show how this helps. So recall, you want to sum over all small sets A 2 to the minus NA, right? So recall that when we had a set A, you can break it up into its two linked components. So the picture is like kind of here, like when you have a set A, you can break it up into its two linked components. And so, yeah, so you just, you sum over all K, the union of K disjoint two linked components. And since their neighborhoods don't intersect, the neighborhood of A is just the sum of the neighborhoods of the AIs. And this is at most just the sum of small two linked 2 to the minus NA raised to K, but then you're counting every set of A1 to AK, K factorial times here. So you just divide by 1 over K factorial. Okay, is that okay? So, and this is, but then this is exactly the expression for E raised to this sum over A2 linked 2 to the minus NA. And yeah, now you have this kind of a sum where you took a sum over all A and you only converted that to the sum over small A's, sorry, two linked A's, split it according to the size of A and neighborhood, and just this is the bound. Use the bound that the lemma gives at this point, and then use the bound that Olson's theorem gives to say that T is at least D, and yeah, this is small. Okay. So these type of computations are not really supposed to be clear at all. Like maybe they might not be clear at all, but now these are very well understood. Like these are the first few terms in the so-called cluster expansion. I'll talk about this a bit more later, but what we are essentially doing with this computation are just looking at the first few terms of what's called the cluster expansion of some function. So yeah, I hope this part is clear, that the lemma implies that what we want is small. Like, so all that's left is to prove the lemma, except I haven't even stated it properly. And this is like the precise formulation. If D satisfies some properties, then the size of script GAG is at most 2 to G minus omega T. Okay, so these are a lot of them, but the point is that I guess the main point is to not be bothered by them, because in the way the problem is set up, these are basically without loss of generality. Right? So it's like if you kind of brush very little under the rug, it's literally this. You literally have a bound on the number of sets A of a given size and whose neighborhoods are of a given size. Okay, so questions? So a bit more of a background of where these kind of bounds come from. So this is like, all this relates to the so-called Sapojenko's graph container lemma. So the precise formulation, again, so this is due to Sapojenko 1987 and recently improved by Khan and Park and explicitly stated by Park, which says if you have a bipartite deregular graph right? And say, just assume that D is much bigger than log n. That satisfies these two conditions is that for every pair of vertices, the co-degree, like the common degree of x and y is small, and every small set has a neighborhood size, at least its size times, or rather, I can just put this for free, at least its closure times at least 1 plus some omega of log cube du over d. Again, so this is not very important, but the point is that every set expands at least, has a minimum bound on the expansion. Then you have this kind of a guarantee that the number of sets of a given size and neighborhood of a given size is at most something. Okay. And what was the motivation of Sapozhenko? The context here is that, like, QD is the hypercube graph. So the vertex set is just all binary strings of size d, and the edge relation is if they differ in exactly one coordinate. So this was a theorem of Korshinov and Sapozhenko from slightly before, which basically asymptotically computes the number of independent sets of the hypercube. It's asymptotically equal to 2 times square root of e times this 2 to the d minus 1, right? So if you stare at it, QD is bipartite. You have all strings of even Hamming weight and all strings of odd Hamming weight, and it's deregular. Okay, so this part and this part comes from taking all independent sets here and here. So that's where both of these terms comes from. Okay, the square root of E actually comes from counting independent sets that actually take part in both even and odd. And the idea is, look, the upper bound on independent set is like you're summing over all A subsets of x2 to the minus na, right? So the square root of E comes when you sum over all A, which are just some large but fixed constant. Right? So what Sapozhenko, like what Korshinov and Sapozhenko say is that most of the independent sets in a hypercube don't come from subsets of even or odd, but they have a few more independent sets. And these few more independent sets are those which either contain a constant number of independent sets on even and all possible subsets of odd, or a constant number of vertices in odd and all possible subsets are even. So this does not give a very, like, does not just like give a very neat description of independent sets, but it's like it's really informative. And yeah, and the idea is that later on in what we called Sapozhenko's graph container lemma, he basically gave a way to rederive this result in a very general way. Like, so this graph container lemma that I stated has nothing to do with, like, okay, like it has some properties that it makes use of some properties that the hypercube has, but not much beyond some minimum expansion and small co-degree. Okay, and I guess it should also state, like, Sapozhenko is like much more general than this. Right, so, but yeah, so this is a formulation that is like useful to us when we talk about deregular graphs. Okay, so, and this is like, yeah, so this is like, this was so-called graph container method, and it's pretty useful, and it showed up in a bunch of different places. So in particular, so among the many applications, so this kind of showed like a phase an upper bound on the phase transition of the hardcore model in the integer lattice. This is by Galvin and Kahn. This is the lower bound for mixing time of global dynamics in the hardcore model of bipartite graphs. So again, this is like an algorithmic, this is a proof that certain algorithms don't mix quickly. This is due to Galvin and Tetali. It helps count the number of 3 colorings in the hypercube, proper 3 colorings. This is due to Galvin. The proper 4 colorings is due to Kahn and Park, and like this was settled for every constant Q, the number of Q colorings due to Jensen, Matthew Jensen, Peter Kivash. So this is, and this method also helped in counting some other information about the hypercube. Like if you want to not count the independent sets, but the number of maximal independent sets. So this was done by Kahn and Park, and it also gives like extremely detailed descriptions of independent sets of a given size and structure in the hypercube. So I guess this was started by Galvin and really done for the whole range of this method by Jensen and Perkins. So this kind of like, so it uses this aforementioned cluster expansion. It uses like whatever calculations we did before, it studies them extremely carefully and it pulls out a lot more information about these independent sets. And not only that, like it also helps you to compute the number of like middle layer independent sets. Like these are independent sets in the middle two layers of the hypercube, and things that don't have anything to do with the hypercube at all, which is the number of intersecting families of n choose k. Like these are the number of uniform intersecting families, and this is like very recent, like by Balog, Garcia, Lee, and Wagner, and actually many more. So the point is that I hope this is clear is that this is a pretty useful method, and a lot of these papers are pretty recent. So this, I guess, kind of a recent surge of applications of this method. Okay. So anyway, so back to Sapajenko. What is it saying is that if I can get, so it has two conditions. One is that the code degree is constant. So this is, again, this condition is not like super important. But the main condition to focus on is it requires this from the graph, that every set A has some kind of an expansion. And this is not true in Cayley graphs. Okay. And I'll just describe why it's not true, but most of the work actually goes in overcoming this hurdle. So let me just quickly tell you why, for example, these things don't hold in Cayley graphs. Look at the Cayley graph on Z mod 2n, right? And the set of generators is a bunch of consecutive odd numbers. So this is just a bunch of consecutive odd numbers. So if I draw the graph, it will be clearer. So in Z mod 2n, there are even elements and odd elements, which mean exactly what you think. And the neighbors of a vertex U are a set of consecutive D odd, odd elements from the other side. So this is a Cayley graph. Okay? And there are sets A such that the size of the neighborhood of A is kind of exactly size of A plus D. Right? So as A gets larger, this is not good enough for Sapajenko, the techniques to work. Okay, so like there are clearly graphs that don't expand. And by the way, so recall in the conjecture, I told that, I told you I'll describe the graph for which I believe has the maximum number of independents among Cayley graphs. I think it's this graph. So in the conjecture, if D is something like 2 plus epsilon times log n, then so that's what the conjecture states, is that this is the Cayley graph with the most independence. It's among all the regular graphs. Okay, so again, so let's recall the basic subset notation again. I'll talk a bit more detail. A plus D for, again, A and D subsets of the abelian group is just the sum of A and X for all A and X and D. So stare at it for a minute. In Cayley graph, the neighborhood of a set A is A plus D, and the neighborhood square, like the second neighborhood, is A plus 2D and so on. Right? So that's how. So that's one way to express the neighborhood. And so the expansion of the Cayley graph is kind of how fast these subsets grow. And again, so just to recall again, we know from Olson that if it's A is small, there's some kind of subset growth, except it's not enough. And I want to talk a bit about the proof ideas, but before that, for a vertex U, its neighborhood is just U plus D, and its neighborhood square is just U plus 2D. So the size of this is just D plus D. The second neighborhood of a vertex is just this. It depends only on the set of generators. Let's call that D sub 2. This is just for some basic notation of the for some basic proof ideas. Are there any questions before we move on to the proof ideas? This is a good place to start. Okay, so I'll just talk a bit about the proof ideas. Is that okay? Consider a set A and its neighborhood NA. Right? So there are some. So again, so the lemma that the proof ideas I want to discuss are kind of 2 to the like is that the script G of A and G is at most 2 to the G sizes of A and its neighborhood. Okay. And here is like I'll just tell something that are involved in the proof is that you have a set A and you have its neighborhood. So look at all the vertices of the neighborhood that see vertices outside A, so that are connected to vertices outside A. Okay. So this set is called the boundary of A. So all the sets in neighborhood of A who see vertices outside A, or rather who see vertices outside the closure of A. Okay. So the main sublemma is that there is a set of subsets of Y, there's a family of subsets of Y, such that each element, again, the quantities are not very important, but what it says is that each element of this family is small. It has some bounded size. The family itself is small. Again, the quantities are not very important. But the point is that for every small two-linked A, there is some set in this family that contains the boundary of A. Right? And this is kind of much smaller than you would expect from any naive bound. So it's like kind of a container for the all the boundaries. And the point is that the boundary actually contains a lot of information about A. So just let's stare at this. Here is A, and here is the C that contains this boundary promised by this lemma. Every vertex outside C, it's the color. So every vertex outside C has all of its neighbors either outside of A closure or all of its neighbors inside A closure. That's kind of what that's what kind of defines the boundary. And if C contains a boundary, then every vertex outside the boundary has neighbors. All of its neighbors are either inside A or outside A. Okay. And when you have this kind of a thing, you do the natural operation. You just squish these vertices along with their neighborhood. So yeah, so the idea is that vertices outside, so both of these kind of vertices, kind of give very little information about the set itself. So what you do is just squish them. So just while there is like just the formal algorithm is like if you have an element which is not in C, just remove the element from Y, remove all of its neighbors from X, and like replace with a new vertex whose neighbors are like you squish this vertex. So pictorially, this is what happens. Here is V, here is the neighbor, here is its neighborhood, and here is I guess like its two neighborhood. So what you do is you just squish V with its neighbors to make this V prime and have the same two neighborhood. And so just keep doing this operation. And I guess at this point it's just pictures, but what's left is that you have after squishing all these parts, on the right hand side, you only have C. On the left hand side, you have some subset of vertices X. All you know is that the size of X prime and the size of C in particular is bounded, just given by the lemma. So here is the hope, is that for whatever you had as A before corresponds to again some subset in this squished graph, and whatever subset you had as its neighborhood corresponds to some subset in this squished graph. And because it's a Cayley graph, something happens like the neighborhood of A is still at least A plus T. This part is preserved. But what the key is that A itself is so small because it's a very tiny graph. A itself is so small that this is at least A times 1 plus. So this is whatever Sapochenko requires to make the proof work. So the hope is that A itself is so small that the conditions previously required just hold. Okay. And yeah, so this is kind of enough. Like if this kind of a thing happens, is enough for Sapajenko. But it's not that simple, but this really provides a start on how to like use existing techniques on this problem. And so yeah, so I'll just state the lemma once again. That was like the point here is that there is a subset Y which says that every element in it is small, the size of the family itself is small, and every small two-linked A, like its boundary is captured by some element of this family. Okay. So this is, I guess, like the main thing. And yeah, so yeah, I thought if I reach here, I'll talk a bit more about details, but I don't think I should. So yeah, so this is so this is the end of the thing. So yeah, unless there are questions, that's all I want to say about the presentation.
Thank you, Aditya. That was very well explained.
Yeah, sorry about the internet problems. On the one, like, yeah, this doesn't always happen, but when it happens,
yeah.
Cool.
Any questions?
So I have just one remark. I think everything extends to, or there is a reduction to cover all vertex transitive graphs, isn't there?
No, unfortunately, no. I don't know how to reduce it. Like, really, the Cayley-ness of this is used. So what's used is like the Plünnecke-Rusza-Petridis inequality. So we really need this type of like a very strong form of this type of a theorem.
Well, I understand that that's what you use in the proof, but there is this result, if I'm not mistaken, that if you have a vertex transitive graph, then you can always find a suitable blow-up, which which becomes a Cayley graph. Okay.
Oh, no.
And,
not.
And okay, now you need an Abelian group. So okay, so that's something I'm not claiming anymore. But then if you could, then you could control the number of independent sets there, and that would give you the correct bound in the original vertex transit.
Yeah.
Whose result is this, Jan?
It's something algebras are taught in kindergarten, but again, I think you don't have a guarantee. This vertex transitivity. Okay, I have a paper where I mentioned that, so I can send you a link for that.
Yeah, that's great. Thank you.
So we definitely believe that this should hold more generally, but at this moment we really need this like so we are kind of limited by our use of this thing.
Yes, okay. But again, I'm taking it back just because this vertex transitivity, I don't think there is any notion of commutative vertex transitive graphs.
So the question is that improved upper bounds just using expansion. So what do you mean? So you mean, so you don't have expansion in Cayley graphs, right?
Can I? So what I mean is that, I mean, there were some places where you were using some form of expansion, and then I'm just wondering whether for D-regular expanders, I mean, just the basic combinatorial definition of expansion, any upper bound is known. I mean, I'm not asking whether you are proving it because you're using, I understand that you're proving for Cayley graphs, but I'm not familiar with this literature so much. Just, I mean, I think at some point you even asked this, whether when you have, okay, the graphs which maximize the number, deregular graphs which maximize independent sets are, so, they're these disjoint complete bipartite graphs. So I'm just asking whether anything is known for, whether you are aware of any upper bound for expanders, where you don't know anything about the structure, I mean, how this expander is constructed, just that it expands.
Right, you want something with a weaker expansion guarantee, is it? Like Sapochenko proves it for some kind of expander. You just want if it like holds for weaker expanders, like if there's like less expansion guarantees. That
then maybe I missed this. So okay, so
we know this kind of things. If for every A, the size of the neighborhood of A is at least A times, I guess, 1 plus order log square D over D, the omega log square D over D, then this kind of container method works.
I see. Okay, so I didn't pay attention very carefully. Okay, I see. So I guess I'm asking whether one can use weaker expansion to prove some of it.
Yeah, I don't know. So I don't think there is, but yes, this. Yeah, I don't know enough to rule it out, but I don't think there's existing.
All right, thanks.
Any more questions? Maybe you can mention again some of the remaining open problems.
Yeah, so the main thing is the conjecture is that firstly, like this should hold for B bigger than 2 plus epsilon times log n, and G is Cayley, of course, these Abelian Cayley graph. Then the number of independent sets is at most 2 to the n plus 1 times 1 plus the of 1. And again, I think the tight example is this Z mod 2n, where you pick all even elements and odd elements, and the neighborhood of a vertex is a bunch of consecutive odd elements. Okay. And to try and extend it to a more general family of graphs, just look at this like this one-sided Cayley graph, where you take two copies of a group, say let's say F1 and F2, and you just put for every vertex U, you put neighborhood, like you put a neighborhood to U plus B. You just don't do it the other way around too. So this is like a Cayley graph, but it's like asymmetric with respect to both sides. So I mean, like the point is, I believe this should hold with a lot more generality than just Abelian Cayley graphs. But this is one example to, I guess, try if you want to extend it beyond. So this, okay, in our method, this requires understanding things like the size of A plus B versus size of A minus B. But yeah, maybe you don't need to go through this.
Thanks a lot. Whoever is here, maybe we can give a round of applause to Aditya.
What could be the next thing?